Yes, I'm Adam Suhl. I am here to present the blast radius attack. This is joint work with, in alphabetical order, Sharon Goldberg, Miro, Nadia Heninger, Mike Milano, Dan Shumow, Marc Stevens, and myself. Our attack allows a network adversary with a machine in the middle to forge arbitrary radius responses, which in particular means you can log into a victim device that's using radius with completely bogus credentials. This is not an implementation vulnerability, it's a vulnerability in the protocol itself, namely that radius uses packet authentication based on MD5. But let's back up a bit. What is radius? Radius is the protocol for authentication, authorization, and accounting, or AAA. If you have a device that you want to be able to log into over the network, but have auth outsourced to some separate server, the device and the server are probably speaking radius to each other. When you log into the device, you're not speaking radius. That can be over HTTP, SSH, whatever. The device and the server speak radius to each other to decide whether or not you can log in. But why should we care? Does anything actually use radius? Turns out, yes. Basically, every piece of network equipment made in the last 25 years supports it. It's used for administrator logins to internet backbone routers. Basically, every non-cable ISP uses it internally. Okta and Duo both use radius as one of the supported ways for integrating their services. It's used for logging into power grid equipment and industrial control systems over a network. And as previously mentioned, Eduroam and other enterprise Wi-Fi networks use 802.1x, which uses Eduroam. But luckily, 802.1x is not vulnerable to our attack due to some 802.1x specific details. So even if you yourself don't use radius, your infrastructure almost certainly does. Radius has been around for a very long time. Unfortunately, it is also using cryptography that has been around for a very long time, namely MD5. MD5 is a hash function that was broken 20 years ago to the day. I believe it was August 16th, 2004, so exactly 20 years ago, funnily enough. But it is still in use in radius because, for one thing, it's backward compatibility. It's very hard to deprecate. But also, among practitioners, it was known that MD5 was broken, but it wasn't known how to break MD5 in the particular way that it's used in the radius protocol. In this work, we show how to break MD5 in the particular way that it's used in the radius protocol. So let's take a look at the radius protocol in more detail. You try to log into a device. The device is acting as a radius client, and it sends an access request to the server saying, hey, here are the details of an attempted login. Should I allow it or reject it? The authentication server sends back either an access accept or an access reject. Can also send an access challenge, but I'm not going to discuss that in this talk. This response from the server is what determines whether you can log into the device or not. And all of this is happening over usually UDP. There is not a TLS tunnel that is wrapping this most of the time. In order to authenticate the response packet, the client and the server have a fixed, pre-configured shared secret that they use with this custom MD5-based MAC construction that we'll get to in a bit. So radius packets all have a 4-byte header that says what type of packet it is, the packet length, that sort of thing. And then requests include a 16-byte random nonce and a list of attributes, things like the username, the password, IP address of device being logged into, that sort of thing. The responses, the access accept, access reject, also have attributes, but instead of having a nonce, they have what's called a response authenticator. This is, as the name suggests, something that is used to authenticate the request. It is intended to be hard to forge. The structure of it is as follows. So when the server is computing the response authenticator for a response packet, it modifies the packet to include the nonce from the request that's being responded to. It appends the shared secret that is known only to the device and the server, and then it hashes the whole thing with MD5. Because the shared secret is known only to the device and the server, this is intended to be hard to forge. And so if the client receives a response packet that has the wrong response authenticator on it, it will just discard the packet. In our attack, we would like to forge an access accept. But as mentioned, we don't know the shared secret, so we can't compute the response authenticator. What we can do is we can create an MD5 collision between an access accept and an access reject, such that even though we don't know what the correct response authenticator will be, we know that it will be the same for both packets. If we can do this and then trick the server into sending the access reject from our collision, we can take the response authenticator on that and copy it onto the access accept. So to summarize our attack, we try to log into a victim device, and it sends an access request, which we intercept. We then compute a colliding pair of packets, one of them in access accept, one of them in access reject, such that even though we don't know what the correct response authenticator will be, we know it will be the same for both packets. We then send a very carefully crafted request to the server that will cause it to reply with exactly the reject packet from our collision. This reject packet will come with the correct response authenticator that the server has computed, which we can then copy onto the accept packet because we know it's valid for that as well. The victim device now sees an access accept packet that has a valid response authenticator and thus grants us access. We've logged in using completely bogus credentials. So that's sort of the high-level overview of the attack. And now let's dive into the details. First, a little background on MD5 collisions. MD5 has been known to be weak since 1993, but the first MD5, the first full collision was found in 2004 by Wang et al. And this is a collision between completely unstructured data that we'll call gibberish. The type of collision that's more useful for attacks, known as a chosen-prefix collision, was published 3 years later in 2007 by Stevens et al. And here, the attacker gets to pick a pair of prefixes, P1 and P2, and then gibberish is found such that P1 concat G1 is a collision with P2 concat G2. This was used in 2009 to create a rogue TLS CA certificate. Now, one interesting property about MD5 is that if you have a collision and you append the same data to both sides of the collision, it doesn't matter what that data is, you will still have a collision. So as we can see here, MD5 of P1 concat G1 concat S equals MD5 of P2 concat G2 concat S for this collision that we found, no matter what S is. This is a very useful property we'll use in a bit. But in terms of MD5 collision history, there's a 15-year period after that where nothing much happens. MD5 is considered dead. Cryptanalysts have focused their attention on SHA-1 instead. Until now, it turns out Radius is still using MD5 in the year 2024. This is surprising considering how widespread Radius is and the fact that MD5 has been known to be weak since around the time I was born. But it wasn't known how to use attacks against MD5 to break Radius until our paper. So let's take a look at that. In order to forge the response authenticator for a packet, the machine in the middle attacker is going to predict the prefixes of what's going into the hash function for an access accept packet and an access reject packet. Then carry out a chosen prefix collision to find gibberish that can be appended to both, leading to a collision. Note that both the server and the client will append the shared secret when computing the response authenticator. And the shared secret is unknown to us. But fortunately, because of the MD5 properties that I mentioned earlier, the hash values are still going to collide no matter what the shared secret is. Access accept now has the same response authenticator as the access reject. And so we can carry out the attack from the previous slide. This makes it sound a lot simpler than it is. And I'm going to discuss two subtle challenges for executing the attack. The first challenge is that the attacker needs to actually trick the server into sending the access reject that includes this long, random-looking gibberish string. This seems very difficult to do, but fortunately, there is this beautiful attribute called proxy state, where you send in your request a long, opaque blob of data, and the server is required to send it back to you unchanged. It can't do anything weird based on the contents of it. This is perfect for our attack. We can take our collision gibberish and put it into the proxy state attribute of a request and get it back in the response. And we actually improve on existing chosen prefix collisions to be able to split the gibberish across multiple proxy state attributes. So we can hide the gibberish in the proxy state attributes of a request. It then gets mirrored back to us in the response. The second challenge is that because the prefixes include the nonce from the request, we cannot pre-compute the collision. We have to do it once we know the nonce from the request. And that means we have time pressure because the Radius client is going to time out. Now I know what you're thinking, MD5 collisions can be computed in seconds on a laptop. Unfortunately, that is only for identical prefix collisions, where the prefix is the same on both sides of the collision. The chosen prefix collisions with different prefixes on both sides of the collision are much more expensive. It took 28 hours for creating the TLS CA certificate back in 2009. When we started the experiment, it took dozens of hours for us to run our attack. We were able to optimize it down to run in less than 5 minutes. To summarize the impact of blast radius, the radius authentication modes PAP, CHAP, and MS-CHAP are all vulnerable. EAP authentication modes, like used in 802.1x, are not generally vulnerable because they mandate using an additional attribute called message authenticator, not to be confused with the response authenticator, that I'll talk about on the next slide. Our attacker requires machine-in-the-middle access. So all deployments that are sending radius traffic over UDP over the open internet are going to be vulnerable. If radius traffic is sent over a IPsec tunnel or a VLAN, then the adversary first needs to obtain access to that network. But this could be useful for lateral movement. So for example, you have access to a network already. You now get access to every device on that network that is using radius. In terms of timeouts, radius client timeouts of about 1 minute are common when multi-factor auth is involved. Our proof of concept takes 5 minutes because that is the maximum configurable timeout on the Cisco ASA box that we did our proof of concept attack against. But our attack parallelizes very well, and it should be possible to bring that down significantly by just spending more resources on it than we did, or even by implementing a hardware implementation of the MD5 collision. Radius is used in many different applications. It's used, for example, for remote access to windmills and power plant controllers. Some of these implementations are very hard to update, which means backward compatibility is a major requirement. Our disclosure process involved over 90 vendors, but it was a fairly smooth process thanks to the help of CERT. In collaboration with vendors, we developed the following mitigations. In the short term, we recommend applications include and verify the message authenticator attribute in all requests and all responses. This attribute authenticates the packet not with MD5, but with HMAC MD5, which is not vulnerable to collisions. Of course, in the long term, the better option is to just wrap it all in TLS. TLS provides very strong confidentiality and integrity guarantees, and there is a current IETF draft that is for radius over TLS. I will conclude with this relevant XKCD, and that is our presentation. Happy to take questions.